I record. I'm so sorry about that. Oh, wow, that's embarrassing. Okay, I will post the Friday recording, and hopefully you get me going through this problem. Until then, I hope you all have carved this in your memories. Okay, so let's talk about BFS first. Okay. So what is breadth first search? So breadth first search and depth first search, you start at a particular node. Okay, so let's start at A. Okay, so what this means is you basically what you do is you take A and you look at A's neighbors. Okay, and then the nodes that you've looked at, you look at their neighbors next in order of when you saw them, just one neighbor away. Okay, and then you just keep going like that. So in other words, the way you explore is you look at A. So you've explored A, and then you look at everything one away from A, and you explore that. And then you look at everything two away from A, and then you explore that. Okay, so this data structure is like a first in, first out kind of thing. Are we familiar with like heaps or like first in, first out data structures? So here is what my data structure looks like. I keep my start node A. Okay, I like to have the heap just here, like a scratchwork when I'm going through this. Okay, it helps you keep organized. So A, and then what I do is I add all my neighbors from A to my data structure. What do I add? B and C. Okay, and so it doesn't matter which order you do it. I usually do it alphabetically because I think that makes the most sense. So now B and C are part of my heap. Oh, by the way, when I'm on this, I will underline. So I'm on A right now, and I've added B and C to the heap. And so I've added all of its neighbors. So I'm done exploring, and I can cross A out of the heap. So A has been popped out of the heap. Now the next element in the heap is B. Okay, when I pop an element, maybe I will erase it. Okay, so B is now the element we are considering. We add all neighbors to the heap. So we add A and B, right? No, that's a trick question. Okay, so I will ask a lot of like trick questions to just, rhetorical questions to make sure you understand concepts. Make sure it'll be very clear. I'm very bad at hiding when I'm trying to throw a trick question. So A has already been explored. Okay, there's a check by it, so we don't add it to the heap. Everything that does not have a check is added to the heap. So D is added to the heap. We are done exploring D because we've added all its neighbors. So we check it off and then we pop it out of the heap. What's next? C. Notice that it's not D. It could have been D, right? And then we explore E and then C. No, that's not what we do. Because it's first in, first out. We are now considering C. So C. What neighbors do we add? We don't add A because it's been explored. We don't add D because, I mean, we can add D. Why not? Okay. We'll see that like, okay, we'll add D, okay? And then we also add E. So we've added all its neighbors. Check it off. Then, by the way, for those of you who, I mean, most of you inevitably will like do some kind of thing in like software engineering or programming. If you want to implement this, it's important to like keep like an explored array. So like a Boolean array of explored saying this has been checked off. Okay, that's an implementation detail. D. Now what? So now we consider D. So we take it on the heap and we add all its neighbors. Okay, well, we haven't. None of the neighbors. Okay, we can add E because B, C have already been explored. So we add E to the heap. I'm sure you can imagine a smart way to keep like duplicates off the heap to kind of save runtime a little bit. But for right now, we'll just keep things simple. So we've added all the neighbors of B. Check. Delete it off. Now we consider D, but wait, it's already been explored. So before we do anything, we know we've already explored D, so we can delete it off. And so now the same thing with E, or not the same thing. We have a new thing. So we look at all its neighbors. There might have been a neighbor here, like F, but in this graph, there was nothing. So we add all its neighbors, which entails adding nothing to the heap, okay? Because everything next to it has already been explored. We delete it from the heap, of course, after marking that it's been explored. And then the last one is E, which has already been explored. So once we consider it on the heap, we already know we can pop it off. Okay, and so that's depth first search. It's pretty much maintaining this heap data structure and being principled with how you traverse it. Okay, so what order do we go? We went A, B, C, D, E. Definitely intentional. Okay, so we went A, which is 0 far away from A in terms of the number of edges. Then B and C, which are both 1 far away, and then D and E, which are both 2 far away. So the distance is 0, 1, 1, and then 2, 2. Okay. Now, of course, A to C to D to E is actually, it's 3 distance away. But the shortest distance is 2. Okay. So BFS, what does BFS do? BFS is shortest path with equal edge weights. So if all the edge weights were 1, then BFS would find the shortest path. Okay, because it's just the fewest number of edges to reach any particular vertex. Okay. All right. Any questions about BFS? Have we done like Dijkstra's algorithm in a previous class? You guys have gone over Dijkstra's algorithm? Okay, yeah. I mean, Dijkstra's algorithm also has some kind of heap in it. So I mean, BFS is like a bare bones version of Dijkstra's algorithm. Dijkstra's algorithm, you have to consider more complicated things, but like different edge weights, for example. Yeah. Okay. So now what? Now we're going to talk about BFS. Okay. So let me erase any questions about BFS again? No? Okay. I'll erase markers. We'll use the same graph. So BFS uses the heap. DFS is going to use, does anyone know? A stack. So what is a stack? So like it's a stack of books. If you put down a book and then another book and another book and you try to take off a book, you will take the book from the top. Unless you want to be chaotic, of course, but like just safely, you want to take the book from the top. So it's last in, first out. Okay. So the DFS is a stack E. Interesting. My spelling has, okay, whatever. So let's say this is the bottom of the stack. Okay. And then the stack goes up and then we take elements from the top. So again, A is our first element. Okay. We start at A. We push A onto the stack. Or well, we don't need to push A on the stack. We'll push the neighbors on first. Okay, so we look at all neighbors of A. Okay, and we add them to the stack. So B and C go onto the stack. All right, and so once we've done that, okay, once we've added all the neighbors to the stack and we've done our whatever, like you should realize that each of these algorithms, okay, is like a structure. It's not an algorithm in and of itself. Like for each of these nodes, you want to do something to it. Okay, like find the node which has, like, let's say each node has like a value on it. Okay, find the node with the smallest value. What you can do is you can do a BFS traversal and keep it running minimum. So there's like some sub procedures that you do in each one of these nodes usually. The exploration procedure is not just add it onto the stack and keep moving, because you want to have some kind of versatility to this algorithm. Okay. Anyways, so we add B and C to the stack, and then once that's done, we're done with A. So now we consider C. Okay, we consider the top element of the stack. Here, I guess I will circle the element of the stack that we're considering. Okay, so we take C. We take C out of the stack. So now we're considering C. So we add all of its neighbors that have not been explored. explored yet. That's D and E. Okay, and so we add those to the stack. All right, and then we're done exploring C. So the next thing we do is E. Okay, so we take E out of the stack. And we add all of its neighbors that haven't been explored yet. Well, we would add D, I suppose. And then we're done. Okay. And then we take D out of the stack. We add all of its neighbors that haven't been explored. That's B. Okay. And then we're done exploring D. Then we take B out of the stack. Oh, I circled the wrong thing. Okay. B, we take B out of the stack. Okay. And then we add all of its neighbors that haven't been explored. That's none of them. So we add nothing to the stack. And then we're done exploring B. And then we pop D out of the stack, but we realize it's already been explored. So we just pop it out and do nothing. B has already been explored. We pop it out and we do nothing. Okay. And so that's the depth first traversal or depth first search. So you just, once you go down like an edge, you just keep going down that rabbit hole essentially until you can't explore anything else. Okay. So I like to say DFS stands for distracted first search. That's one way we can look at it. Okay. So the traversal is A to C to E to D to B. Okay. So like one way, so this is what it's like for like undirected graphs, but like in directed graphs, you can kind of go about it like yourself, and you can see that like once, oh, excuse me. I think I made a mistake here. Okay, so I guess you could think of it as implementing it by a stack, but let's think about it another way. Okay. You can also implement it like by a recursive algorithm. Okay. So what is that recursive? And you could basically use like the structure of your program, like the recursion as a stack in and of itself. Like you keep calling, and once one frame is done calling, you go to the previous thing where you called that frame, and then that forms a stack in the program. Okay. So what you can do is you can start at A. Okay. And then you could go to B. So I'll put like a number to the left when I start there, okay? And like when I first touch a node, I'll put the number to the left. And when I'm done exploring that node, I'll put a number to the right, okay? So 1, I start at A. And let's say I go to B next. That's 2, okay? And then I'm only done exploring A if all of its neighbors have been are done being explored, okay? That is, they have a number to the right. So I'm not done with B. So as long as I'm not done with B, I add another node. And so I start exploring D over here. Okay. And so I'm not done with D. I have to check C and E. So I'll break ties alphabetically. 4. Okay. I add this to the left. But I don't know if this is in the textbook or not. I just think this is a useful way that I personally like to keep track of this stuff. Okay. And it's mathematically kind of interesting as well. But anyways, I start exploring C. Am I done with C yet? No, because there's a neighbor that there's actually 2 neighbors that have not been explored. Oh well, just one neighbor, I should say, because the other 2 have left numbers on. Okay. So C to E, and then I add 5. So is E done? Well, all of its neighbors have been explored. So what I do now is I add a right node, or a right number, sorry. That's 6, okay? So with C, Have all of its neighbors been touched? Yes, they have. So 7. Okay. And then I recurse back where I came from, which is D. Have all of D's like neighbors been touched? Yeah. All right. And then I go back up to B, and 9, and then 10. Okay. So if you were going to form like a DFS tree of your traversals, so let's say every edge you take in the traversal, the first edge we took was this, and then this, and this, and then this, right? What do we get? A, B, C, D, E. Oh, no, this is D. Excuse me. This forms a tree. Okay. Does that make sense? Why does it form a tree? Well, remember, a tree is connected and acyclic. If this graph is connected, then we'll reach every node, right? By adding an edge to a previously connected node. Why is it acyclic? Well, we never add an edge to something that's already in the tree. That is, we never add an edge to something that's already been explored. So that's why DFS and BFS really, they both form trees. Any of these graph traversal algorithms form trees. Well, we can add an arrow to indicate the direction in which we came. So notice, why is this kind of useful to maintain a left and a right number? Well, there's a lot of things you can do with it. Okay. For example, one thing you can do is you look at E. Okay. So let's look at the number line. So this is 3, 4, 5, 6, 7, 8. Okay. 4, 5, 6, 7, 8. All right. So what is C's left and right number? Okay, it's 4 to 7. Okay. This is C over here, and D's left and right number is 5 and 6. Okay, so we notice that. Oh no, sorry, this is E. Pardon me. Now, okay, C and E. We notice that in this DFS tree, E is the descendant of C. Okay, E is the descendant of C. C is the ancestor of E. So therefore, like the range of E is contained within the range of C. All right. So let's look at another example for that. By the way, I hope you all don't mind me giving you extra information, right? We're all good with that. I think it's pretty awesome. Because like, yeah, again, anyone could just read you the answers. We're both here to learn a bit more. So, okay. So A, B, C. Okay. B is the descendant of A. C is the descendant of A. B and C are not the descendants of each other, nor are they the ancestors of each other, right? So let's look at what these pre and post numbers look like. That's what they're called, pre and post numbers. So on the left, we add 1. B or C, pick your favorite. 2. We're done with B. 3. Are we done with A? No, we got a neighbor over here. 4. Yeah. And then we're done with C. So 5. And now we go back up to A. Are we done with A now? Yeah, we are done with A. So let me create some space here. Okay. 1 to 6. This is A. B is 2 to 3. And C is 4 to 5. They're both, of course, contained within A. Okay, so this is a neat procedure to figure out like what's the ancestor and what is the descendant in like this directed graph format. Okay, so that's one example of how useful DFS is. Okay, I'm saying this because I imagine a lot of you are going to have interviews sometime soon, either this year or next year, and like who doesn't like a few extra tricks in their bag, right? So can teach you this neat graph technique. Okay, wait, well, do you have any questions about DFS yet? Okay. All right. So now let's talk about topological sort. Okay. Have we ever encountered topological sort before? Okay, I can imagine. Yeah, you probably don't learn in data structures. I will say it sounds a lot more like complicated than it is. It is explaining a rather simple concept. It sounds like the thing like, oh yeah, coffee is equal to a donut. Like that's topology, but this is different. Okay, has everyone seen that coffee equals donut thing? Okay, so the idea is that like this has nothing to do with algorithms. Okay, like we need a small break from algorithms. This is a coffee. Or this is a donut. Excuse me. I need a coffee. This is a coffee mug. Okay. Can I draw? Okay, there we go. This is a coffee mug. And the idea is like you can like kind of, if this is made out of Play-Doh, for example, this hole is equal to this hole, and you can like kind of like mold this into being equal to this donut without either creating a new hole or like sealing up a hole. Okay. So or like breaking it into two pieces or like ripping it or something. That's topology. We're not going to talk about topology, although I think that's kind of funny. We're going to talk about topological sort. So we've all had like to-do lists, right? Like we need to do this and then we need to do this. So obviously some things must come before others in the to-do list. For example, I couldn't teach section without, for example, studying like preparing section. So let's say my to-do list was like prepare section, teach section. I could, well, I could teach section without preparing, but that would be awful. So you have to prepare section first and then teach section. Okay, so there's this kind of like order on things. Okay. So this is brush teeth. This is wake up. This is get dressed. And this is leave home. Okay, so in order to get dressed, you need to wake up first. In order to brush your teeth, you need to wake up first. Okay. In order to leave home, you ideally you need to get dressed and brush your teeth. Okay. So this is like some kind of dependence chart, right? So topological sort, basically, what it does is let's call this 1, 2, 3, 4. Does it matter whether we, I mean, based on this diagram, does it matter whether we get dressed or brush our teeth first? No, because we don't need to brush our teeth to get dressed, or we don't need to get dressed to brush our teeth. So it doesn't matter. So topological sort basically takes something like this, okay, and creates an ordering. This is one possible topological sort ordering. 1, 2, 3, 4, such that, okay, so if there is a path from node 1 to node 4, then we must do node 1 before doing node 4. Okay, does that make sense? Because every previous thing, we need to do 1 before we do 2, and we need to do 2 before we do 4. And so if there's a path from A to B, we need to do A before doing B. That's what topological sort is. Another possible topological sorting is 1, 2, 1, 3, 2, 4. Doesn't matter if we do 2 or 3 first. We just need to do both before we do 4. Okay, so topological sort takes this what do you call it? It takes this I'm blanking. Yes, sorry, this graph, and then you get an order out of it. Okay, but there is a bit of an issue. What if the graph looks like this? You need to leave home before you wake up. Okay, so we can wake up first. But wait, we need to leave home to wake up. Okay, then let's leave home first. But we need to wake up before we leave home. So that's an issue. You can't have a cyclic dependence because where do you start, right? So for that reason, we require this to be what we call a DAG. DAG is a directed acyclic graph. We require it to be directed because we want an order. Which one do I do first? If there's an undirected edge, there's ambiguity there, right? They're in some sense both equal, but here there's an order. So we require it to be directed, and we require it to be acyclic. That is, no cyclical dependencies. Okay? And you'll often hear people, people refer to this as a source. Okay, so for example, a vertex that has nothing coming into it is a source. What does that mean if it has nothing coming into it? It doesn't depend on anything. Okay, it doesn't depend on, you don't have to do something before you do it. Okay, so that's a source. Can a graph have multiple sources? Sure. This is also a source, right? And you will hear people refer to this as a sink. The opposite of a source, nothing goes out of it. So it's something that you do near the end of your list. Okay? A source and a sink. How much time do we have? Okay. So you all have this thing at UT where you like leave early before classes, like 5 minutes ahead of time. Okay, I was going to talk about something extra, but I think maybe this is a bit too much. Let's just go to lecture. Okay, so I hope you all enjoyed this kind of impromptu mini lecture, but if you have any questions, feel free to ask me. Excuse me. Oh, well, thank you. Oh, yeah, so it is always okay to head out whenever you want, because this stuff is being recorded. Of course, it would be best if you could like ask questions while you were there. But just feel free to head out like on your own timetable. Okay. All right, I'll see you all.